we're going to do it in dynamics here now for cases where you can neglect, where there is no rotation, but it's going to be the same path. So we're going to apply F equal ma in rectangular coordinates, in curvilinear coordinates, in polar coordinates, and so we're going to look at the system of coordinates again. So what is there to know? So as we know, what we're studying is almost 300 years old, right? The laws of Newton. So what are the laws of Newton?
Physics.
So there is the third law. Okay, we don't have to do them in order. Newton was the first. So there is the third law, which is very easy to enunciate, but actually it's a bit tricky to use sometimes. It's not as easy as you might think it is. Well, you've been using it in physics, so you know that sometimes there are some tricky cases. So we have to be careful. We're going to see that again. So basically, it is if there is a force acting on A by B, there is an equal and opposite force acting on B by A. So I won't do this on a regular basis, but let me do it here. We can use labels here. So this means the force on A by B. And it's equal to minus the force on A by A. So that's the third law of Newton, which works pretty good. It's not always true, of course, because if you take, for instance, the sun on the Earth, of course the sun is attracting the Earth. So the Earth is also attracting the sun. That's what this says. But there is a huge space in between. So if the sun were to disappear, the force acting on the Earth will not just disappear right away as well, because the action needs some time to propagate all the way to the Earth. So you cannot say that you have this instantaneously. But at our scale, and for the velocities that we are looking at, it works pretty good. But if you have very fast objects or very distant objects, it's not true. You cannot have an action that can propagate right away to where it is acting. It would go against relativity. Okay, so that's the third. So let's go back up. What's the second?
An object at rest will stay at rest.
You skipped one, that's the first. F equal ma, exactly. So precisely, it is F net is equal to the mass times the acceleration. So that's why we did all of that work in the first, chapter 12, but the first chapter that we studied. Why did we talk about the acceleration? Why did we stop at the acceleration? We didn't look at the derivative of the acceleration. Because of this law. We know that m, the mass times the acceleration, is equal to the net force. And you were giving the first law, Josh. So what is it?
An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside force.
Okay, so that's long to write, but that's what it is, yes. So, well, it's basically embedded in there. That is, if there is no force acting on an object, then it's either moving with a constant velocity, and that velocity can be zero. That's basically what it is. So the first law is Well, it's not a consequence of the second law, but the second law, well, of course it is a consequence, I want to say. It is embedded in the second law. So if F net is equal to 0, well, V is equal to a constant. And it might be 0, that constant. So there is something else to say. Can you use these laws in any frame?
No, it has to be a frame of constant acceleration.
Not constant acceleration, even less than that.
Zero acceleration.
Right, so, well, but what does it mean? Because you measure acceleration with respect to another frame. So it's kind of a postulate. There are frames where these laws are valid. These are called inertial frames. So an inertial frame is a frame where you can apply Newton's laws. So, well, strictly speaking, there's not really any inertial frame out there, but to a very good approximation, you can find one. So for instance, when you study the motion of planets, you can have a frame attached to the sun. When you study the motion of an object in a room like that, you can have a frame attached to the room, and it's going to be an inertial frame. So an inertial frame is a frame where you can apply these laws, and practically speaking, it's going to mean the frame attached to the lab when you do a desktop experiment, a frame attached to the sun when you look at the motion of the planets, a frame attached to the Earth when you look at the, for instance, if you were to do a study of the motion of the wind, the water, so the currents in the ocean and so on. So you could have a frame attached to the Earth, but not rotating with the Earth. So that's what an inertial frame is. So an inertial frame is a frame where you can apply that. And there are infinitely many inertial frames once you have one, because once you have one, any other frame that is just in translation with a constant velocity with respect to the inertial frame is also an inertial frame. So you see, if you have something like that, which is an inertial frame, and you have another frame in there, so z prime, x prime, y prime. The axes do not have to be parallel. I mean, they are here. And it's moving with a constant velocity. So that frame is also inertial. So, but for instance, if you're inside of a car and you study the motion of something inside of the car, and the car is speeding up, or the car is going into a curve, the frame attached to the car is not an inertial frame. And one way to see that, that is, if you were to look at something on the side of the road in your frame, you would see it moving because you're moving with the car. I mean, you would see it accelerating, actually, if you were to do this. To be in a car that is turning, and you look at something on the sidewalk. So this would be wrong, because you would say, oh, there are no net force acting on the object, and then you would see that it is accelerating. So that would not be then an inertial frame. So all of the frames that we're going to use are going to be inertial. You can write Newton's laws, so not in this form, but by adding a term to work in a non-inertial frame. But it's already good enough to know how to do it well in an inertial frame. So we won't have any terms that we add to F equal m. There is another law of Newton beyond that. Which one is it? That guy did a lot.
That's what laws in thermodynamics, is that what you're
Yeah, but in mechanics, yeah.
Talking about his laws of momentum,